All right, everybody, welcome back to Machine Organization and Programming. Today is lecture 20. My lecture schedule has a bit of a wrench thrown in it this week. My son is doing an online summer camp, and he's using my computer. He's actually learning to code. He's doing a Code Kingdoms Minecraft modding camp. But with him using my computer for 4 hours every morning, it's really throwing a wrench into my lecture production schedule. It's making this really challenging to put the lectures together and get them ready to go before 8 a.m. when he takes over my computer. So it's looking like pretty much everything this week is going to be late. No one's actually complained. I don't know if it just bothers me a lot more than it bothers you guys, or if you're just being really patient with me. I appreciate that either way. So here's what we're looking at. I was taking a look at the schedule, and we're not that far off where I want to be. So this week, we're going to wrap up function calls with some practice. We're going to dive into how assembly deals with arrays and structures, and then we'll finish up with security. So I'm hoping to get through arrays by the end of this lecture. I might break it into two pieces. We'll see how quickly this function call practice section goes. And then next week, we've got dynamic memory allocation and cache memories. I'm going to devote an entire week to that. And then for the final week of the class, there's just 3 lectures the week after next. We'll do an introduction to operating systems, and then we have our final exam. The final exam will be available on Thursday of that week. I've got to look up when the final moment you guys can turn something in for me and I still can turn the grades in on time. But I'll have the date coming soon when I figure it out. All right, and then as far as projects go, the next project, I really love it. It's going to be a lot of fun. I'm going to be releasing that later this afternoon. I really hope I get a chance to finish it later this afternoon. Plan was to have it released yesterday, and I'm behind. But I like this one. It's a lot of fun. We're going to be looking at assembly and writing some, examining the assembly code for some simple programs, and then figuring out what they do. So it's more of a puzzle solving than it is a coding exercise. We're going to be looking at some debugging tools also to use as we explore the code. Anyway, then we're only going to have one other project after this. I'm going to combine what I had been planning for projects 5 and 6 into one, just because we're kind of running out of time with the end of the semester approaching rapidly. So we'll have 5 total projects. All right, and without further, let's see, do I have more announcements? Nope, I think that's it. So on the Canvas website, there's a worksheet for function call practices. Go ahead, grab that worksheet. There's some files that go with it if you want to just download the files directly. But my advice would be to actually just pull up the worksheet. The files contain the solutions. So pull up the worksheet and just try and go through this and follow along. So it's going to be sort of a guided learning experience. So I'm going to go over and pull up the worksheet right now. One sec. All right, guys, I've got the very first worksheet problem set up over here. I jumped into a CSL machine, and I'm going to be walking through this in Vim and just making notes just in text files. So I'm not actually going to be writing this out by hand on the printed worksheet. Hopefully I can use this as a way to I can upload the file. You can see what I've done when I get to the very end of it. But I think there's going to be a lot of utility in watching the video, because I'm going to make changes to what's going on in my memory here. So I've got the file here on the left. It's just a simple function that's just going to increment a parameter that's passed and return the incremented parameter. I've got a very simple main function set up. So this is going to declare some space for variable f, store a value in it, increment that, store that back into f, and then we're done. So the question asks, write the assembly code for the increment function. We could do that. We could actually go ahead, delete the rest of main, just put just this much in. We could run the compiler proper, stop after it produces the assembly, and see what comes out. But I think it's a little better as a learning tool to actually leave all of this stuff in there and talk about what's going on, because we're going to need to know what's in memory, how the parameters get passed to this function. So what I've got here set up, and what I'd like you guys to do, is go ahead and make an assembly file and make a memory. If you guys are just doing this on paper, that's perfect. Just take some space and figure out where you're going to do your work. What I'd like you guys to do is use this as a guided learning opportunity. So go ahead, see if you can figure out what the memory is going to look like right before this function is called. what the stack is going to look like. And then go ahead, write the assembly for this. And then I'm going to walk through this in just a second. But definitely pause the video, take the time, see if you can just write this assembly code on your own based on what you've learned from the other videos. So go ahead, pause the video now. I'll be right back when you push play again to go through the solution. All right, I'm back. I'm going to start going through the solution. I'm going to start over here in the assembly file and just think about what's been going on and sort of write in general terms. There's 5 steps involved with every procedure call. So main's going to go do some stuff. It's going to get set up. And then when we get to this procedure call line, we're going to have a setup step. And then after the setup is done, it'll actually call the function. That's going to jump up. And that's going to jump up into the increment function where we're going to have 3 pieces that happen here. We'll have a prologue. We'll set up the memory and get things ready to go. We'll do the function body. And then we'll have an epilogue. Yep, there we go. And that's going to go ahead and take care of making sure the return value's in the right space, that we've restored the stack, we've removed all the local variables we're using, that kind of stuff. And then when we get back, main also was going to have a cleanup or teardown phase before we move on. Now, prologue and epilogue, those terms are widely used throughout the literature with function calling conventions. I've seen them everywhere. Setup and cleanup, the phases that happen before a function call and after a function call, have a lot more names that people use with them. I've heard teardown, cleanup, setup, preparation. So anyway, I'm just going to use setup and cleanup for my terms. That's what I mean by those, but they do have other names out there. All right, so as we start looking at the assembly code for this, we're going to have 2 regions code, one for each function. So I have an increment section and a main function. So the question in the worksheet only really asks about what's going on. What is the assembly code generated for the increment function? But I think it's important that we know what's going on in memory. We need main to set up the memory during this setup phase so that we can understand what's going on. So that's where I'm going to start. I'm going to take a look at what's going on in main, what happens with the stack. So let me make this a little more clear. This is not just memory, but specifically just the stack. Okay, so somewhere down at the bottom of the stack, I'm going to have a base pointer. And that's going to be pointing to the very bottom of main's call stack. And the very bottom most entry in the stack is the operating system stored base pointer. So that way, when the entire function ends, when the entire program ends, we need to return control to the operating system. And so just like every other function, we're storing where do we return, where's the frame that comes before this one. Even though when we're looking at one individual C program, we don't normally think about what goes on at the operating system level, before we ever called this function. Before we ever, main as a function, before we executed the program. So that's what's going to be in the very bottom of main. We also have a stack pointer. I'll draw that in a second, but right now the stack pointer is also pointed to this very bottom of main. There's going to be some stuff that happens because main is kind of special with memory alignment. We want to make sure that everything is lined on one page of memory. So the first couple of steps, I'm going to skip over them. I'll point them out when we actually look at the real code that's generated by this, but I'm going to neglect those right now and just jump right in. The first thing that we need to do is in main, we're going to reserve some space for this variable f. So let's start right here with, actually the very first thing that we'll see is that just like every other function, we're going to push the base pointer, push ABP, and then we move stack pointer into ABP. So that's how I've gotten to this point right here. I've got the stored base pointer, that was the push. And now my base pointer is pointed right here to this memory location. All right, so that's what's going to happen first. Those are the commands I just described to get to this point. Then we're going to reserve some space for this variable f. So to add space to the stack, these are going, so big addresses are lower, stack grows up towards smaller numbers. So I need to take the stack pointer, which is right here at line 14, and move it up. So I'm going to move, let's see here, I want to subtract to do that. And I only need one integer, so I'm going to take an immediate 4 bytes and remove those from the stack pointer. What that's going to do is it's going to move the stack pointer right here. Just a little arrow. And this is where I'm going to store that 10. Okay, right now it's just empty with whatever was in there before. So the next thing I'm going to do is move. And now I need the number 10. That's what I'm storing, $sign for immediate. And the way that assembly is going to figure out where to store it is by using the base pointer. The base pointer is right here on line 14. I need to know that I'm going to be storing this 4 bytes above that. And 4 bytes towards smaller numbers is a -4. Need the parentheses because I'm accessing memory, not just writing it in the base pointer. 4 above the base pointer. And that's where I'm going to stick the 10. So that'll move the 10 in right there. All right, hope that makes sense. All right, after that, we've now finished line 6. This next piece is going to be, so this line's getting divided into many lines. The first part is it's going to do this function call, then it'll come back and do the assignment. So this is actually 2 parts all in one line. So the function call requires a setup. So I'm going to just put that right here. This is the setup part of the function. Phone's going crazy. Sorry about that, guys. Let me mute that. Be right back. Okay, I'm back. Got the setup here. So what's going to happen is the first thing I need to do is get these parameters ready, because there's one parameter right here, variable f, that I need to push onto the stack. And that's exactly what it's going to do. It's just going to push. Let's see, am I in the right mode? Push. It is a 4-byte integer, so push L. And then let's see. What I want to push is a value from a memory location. So I'm going to use the EBP to figure out where that is. So it'll be something in relationship to the stack, to the base pointer. And it looks like it's above it. That's a lower value, and it's 4 bytes away, so I need a -4. And now that I think about it, that should be the exact same thing as what I used before. It's the same memory location. All right, cool. So what that's going to do is it's going to move the stack pointer up to point to right there and push a 10 onto the stack. Right there, and now that's what my memory looks like. So the stack pointer is pointed to that top value right there, and the base pointer is there. After that, we're ready for the function call. So this is the setup phase. Next, we need to call increment. Okay, when we do that, we jump up. We're now going to be looking at assembly code in the increment function. Whoa, hold on, Mike, you're getting ahead of yourself. The call function pushes the return value, and that return value is going to be whatever is on this next line here. So that's going to be, it's going to push the instruction pointer onto the stack. So that'll move the stack pointer up 1, return address. I think I just said return value. I meant return address. And now the stack looks like that. Stack pointer is pointed to return address. This is the very top of main's stack frame. The next line, when we push the base pointer, will be the beginning of increment stack frame. Okay, so we called increment. That pushes the return address. Now we're ready to move up in here. Okay, so let me do this too. So it actually looks like real assembly code. There we go. A little formatting. So the first thing that's going to happen every time we have a function call is going to be this prologue part. And what this is going to do is going to push the base pointer and then move the stack pointer. So just like that. Push the base pointer, move the stack pointer. So that's going to, well, all right, so let's update this. We're pushing something on the stack. So that means the stack pointer, come on, Mike. Why is it not typing? There we go. Stack pointer moves up. And then I'm storing the base pointer right here. So this is the stored mains base pointer. So that moves the stack pointer up to right there. Now the base pointer is still pointed at this original one, but I want to be able to use the value of this register to address the variables. Particularly we're looking at this 10 right here. Let me make a little note right here. This is the F, and this is the parameter. We want to be able to get to this parameter using the base pointer. So the next thing we do is we're going to move the stack pointer into the base pointer. So the stack pointer is right here. So that's going to take this EBP value and move it up also to right here. And there we go. It's going to look like this. So the stack pointer is always going to be pointed to the top here. I just, for space, didn't retain that. But the base pointer is now, after we do this highlighted line, will look like this. All right, cool. So the next thing that's going to happen, so this is the end of the prologue. We've got everything set up. We're not going to be using any registers that we'll need to restore, so I can skip that stuff for this one. So the next thing we need to do is take a look, and we're going to compute x plus 1. So again, this return and x plus 1 are going to be two different things. We need to compute x plus 1 first, and then we'll return it. So to get x plus 1, that's actually going to be a number of steps also. The first thing I need to do is go grab x and store it in a register for doing that calculation. Now I've got my choice of 6 different registers. EAX, EBX, ECX, EDX, ESI, and EDI. So those are my choices. The absolute best choice is EAX because that's where we're going to store the return value. If I do this relatively simple computation in EAX, then the answer is all ready to be returned when I'm done with the function. But I don't have to do that. If I'm writing code, I can do anything I want. The next best choices are ECX and EDX because I don't have to worry about restoring them when I'm done. Those are the ones that are caller stored registers. So if the caller main is using these for anything, it's responsible for storing whatever's in there. I can change them and then not worry about it. Worst choices are EBX, ESI, and EDI because these are callee restored or saved variables. So if I make any changes to a function with the EBX, ESI, or EDI, I'm responsible for storing it and then restoring it before I return to main. So I'm going to go with EAX. That's the one the compiler will pick also. So to do that, I just need to move that value into EAX. Move something into EAX. And now what do I want to move? Okay. So my base pointer is no longer down here. It's not just -4 from the base pointer. Base pointer is moved. And the value I want is stored here. The return address is 4 bytes. This 10 is the parameter I want, is another 4 bytes. So it's 8 bytes bigger than where the base pointer is. So I want 8 from the base pointer. I hope that makes sense. So this gets me to a parameter. So in a function, parameters are positive parameters. They both start with P. Locals are lower in memory, so they're going to be negative. All right. So I've just done this. I've grabbed the X. It's now in memory. In a register. Not just memory. A register. So to finish up, let's see here. This is I've got the prologue. Let me also make one more little note here. This is the body, starting right here. And then, all right, so that looks good to me. All right, now we just need to increment this. So I'm just going to add an immediate 1 to EAX, and that will take care of the x plus 1. And then as far as return goes, a bunch of things would normally happen. Let's see here. This is the epilogue step. So normally we would see something along the lines of leave followed by return. The leave is going to do 2 things for us. It's going to take the stack pointer and rewind it down so that it's pointed right here at the base pointer. Okay. It's actually already there, so it's actually faster. Oh, and then it restores the base pointer. It's actually faster because that's 2 steps to just recognize the stack pointer is already there. This function has no local variables, so instead of using leave, the other choice is to just pop the base pointer, just like that. And when we pop the base pointer, that's going to move the value, this stored mains base pointer, into this register right here, EBP. So that's going to change EBP. So it's going to move this down to right here. And when we pop something, it's removed from the top of the stack. So that line's gone. Cool. Hope that made sense. And then when we return, let's see if we can make more of this fit on the screen. That looks all right. So we call increment. The return line is just going to pop the return address and move it back into the instruction pointer. So that's going to delete the return address and return control now to this line right here. So I'm on line 28. Again, the stack pointer will be up there, top of the stack. Okay, so now this is the cleanup phase. Is that what I called it? Yep, I called it cleanup. So we need to do a couple of things. We need to take care of making sure the return value goes in the right spot. And right now, that return value is in register EAX. So the first thing I'm going to do is move contents of register EAX, and I want to store it where variable f is stored. And that's going to be 4 bytes above the base pointer. And again, this is a local variable domain. Locals are lower, as in like negative numbers, so it's going to be minus. All right, cool. And then to finish up the cleanup, I also need to remove all of my parameters. So to do that, I'm just going to recognize I've just got the one parameter there, and so I'm gonna, let's see, I need to move the stack pointer to a bigger number, so that's just adding 4 bytes to a stack pointer. All right, cool. There's another way I could have done this. That will just delete that line. I could have used a pop, but in general, pop is going to need to move data to one of the registers, and so that's extra work rather than just changing the value of a register. It may overwrite something that we don't want, so we'll almost always see the compiler using the add for to free up space on the stack compared to a pop. I believe it takes, I think it's faster. I'm not entirely sure, it depends on the architecture of the CPU, but I believe it's faster. All right, so once we've done that, this is the end of cleanup, and we're just going to resume normal execution. The only thing that's left is to return 0. So just real quick, that's going to look like this. Insert. We need to move a 0 into EAX, and then return. That should be the end of that. Let's go take a look at what the code that's actually produced when we let the compiler proper run this, and compare to what I got, and just see if I made any mistakes. All right, guys, I ran the compiler, had it stopped with the -s option. I forgot it gives me all of these extra assembler directives, pretty much everything that begins with the dot. I'm going to take a sec, go look up how to turn all those off, and I'll be right back with a better cleaned up version of this. One sec. All right, guys, so this is what I did before, just gcc -s to give me the stop at the after the compiler proper runs, to give me the assembly, and then I opened it up and looked at it. So to turn off all of those assembler directives, I'm on GCC. I want to stop after S. I'm going to be using increment1.c as my file. Compile for 32-bit architecture, and then fno asynchronous unwind tables. That'll get rid of those tables. fno-pie, and finally fno stack protector. Okay, let me see if I have any typos there. So that's what we're looking for. We're going to turn off all those extra options, and then I can go back up and just take a look at the assembly. Much shorter. All right, went from 80 lines to 40. In each of these functions, we can see that all of those assembler directives have now been removed. All right, so let's take a look at this. Let me pull up my version right next to this, side by side. So, vertical split. Man, what did I call it? Assembly.txt? Yep, okay, so this is what I came up with. All right, so let's start with main right here and main right here. So the first thing, we push the base pointer Line 21 pushes the base pointer. Stack pointer, base pointer. Looks good. Oh, and again, okay, so I reserved exactly 4 bytes for the variable f. And again, main is C is a big fan of having things aligned and will often reserve more space, multiples of 16, for variables, and then only use a small portion of that. So that's exactly what it's done here. It's reserved some extra space. When we go ahead and do then we move 10, the immediate value, into the same location. So I just put it right there on the stack in the reserved location for f. Then we pushed the parameter. We called the function. When we were all done with that, we removed the let's see, is that how I did it? Looks like they did this in the reverse order. Yep, so they cleared the stack first and then took care of the return value. I did it backwards. And then we put 0 into EAX, getting ready to return, and then returned. And I left out the leave. I forgot to clean up my memory when I was all done with this. All right, one little oversight there. So, all right, let's take a look at the function next. So again, we push the base pointer. I did that in line 11. Then we move the stack pointer into the base pointer so that the base pointer now points to the bottom of the stack. That's line 12 in mine. Then we grabbed the parameter that we pushed, stored in EX. And again, just like I predicted, the compiler is going to choose the best possible register for this. And because EX is where we store the return value, it's going to choose that one to do the math. Add an immediate 1 to that, and then pop the base pointer in preparation for returning. It didn't use leave here. It did go with the simpler version because there are no local variables. And then we returned. So I feel like other than that leave, which I neglected, sorry about that, I feel like I did a pretty good job. Hopefully the explanation was useful. I hope you guys took the time to go through this and give this a shot on your own before you listen to the explanation. I do want to do one more thing real quick. Let me get out of all this. Quit all. I want to actually run this entirely, and we'll take a look at the disassembled code. So to do that, GCC output, I'm going to store this in increment 1. Increment 1.c. Whoops, M32. So this will actually produce the entire program. I should now have an increment 1 there. obj dump disassemble, and I want to take a look at increment 1. So this is going to go through, look at the binary code we've generated, disassemble that, and come up with the instructions. There's actually a lot here. Hold on, let me put this in a file. We'll go back over to Vim and we'll take a look at it. So this is increment 1 dump text. Vim. So there we go. Now I can look at this in a real editor and make some comments. So this is what happens. We've compiled the code all the way to binary, and this is taking a look at all of those bytes and going back and turning them back into their parent assembly instructions. So this leftmost column right here is going to be the actual byte. Then these are the values corresponding to each command. So we can see this first command, the NBR32, is actually taking up 4 bytes. They're not all the same. Push EBX is a 1 byte command. And we can see that this is at location 1004. At 1005, we've got the subtract command, which is a 3 byte command. We're subtracting 8. I can actually see the value here that we subtracted right there. Okay, so let's take a look at these different sections. Somewhere in here, we should have a main and an increment. Okay, here we go, down at the bottom. So there's a lot of other stuff going on that's going to help set things up for function calls, and the operating system needs things to work a certain way. Memory alignment needs to, so a lot of those things are taking care of details like that. But somewhere in here, we're going to have a main, and we'll have the functions also. So we can take a look at exactly what really happened. So we can see that we started by pushing EBP. We moved the stack pointer. We subtracted 10. And everything here is in hex. So again, it still reserved all 16 bytes. So we're subtracting from the stack pointer. This is reserving the space for local variables. And then we stored, let's see. Yep, we stored 10, which is A in hexadecimal. It did some other things here. I'm not really sure what's going on with that. When we pushed this and then called the function, and we can see that what it's got here, call, is actually a memory address. This is the address 11AD where increment is stored in memory. That's the very first address, the first byte of the instructions is stored right there, that F3. And that's what we're actually calling. This call jumps to that location. It's an unconditional jump with a restore, with a push of the return address. And it's just letting me know here that this is the name of the function. Okay, and then when we're all done, we did that cleanup. Yeah, so this is actually very similar to what we were looking at with the just when we read the assembly produced by the compiler directly. So, but a valuable tool if you are looking at perhaps a homework problem where you've been given compiled code and are asked to figure out what it does. That's a hint. Next homework will be released soon, I promise. All right, I'm going to go grab the next example, the next worksheet problem, and do the same thing again. So one sec while I go prepare that. All right, guys, I got the second example all set up, ready to go. It's another increment function, but this one is going to take advantage of pointers to make the same thing happen as a call by reference or instead of or call by pointer instead of just call by value. So in main, I'm declaring that same variable f equals 10. I'm going to use increment, but instead of returning the value, I'm just going to give it the address of f. So essentially I'm using pointers here. I see I have a pointer to x as my parameter in increment. And then this line is going to dereference x, add 1 to it, and store it in that memory location. All right, so the question asks on the worksheet, what is the assembly created for the increment function? And again, I've got this in the bigger context with a main function. And I'm just going to walk through and talk about all of this again. I think it's useful. I hope you guys learned stuff from this. And it's we haven't done a good example yet that focused on using pointers as a method to pass parameters. So this will have some new content in it also. All right, here's the idea. So we're going to start off with main. And I left, this is the same, basically the same file. I just cleared out the stuff we don't need. So as I go through this again, it's fresh and we can just add to it. So the first thing that's going to happen is we're going to get set up range for the stack. So we'll push the base pointer. That's going to take the operating system stored base pointer and store it here. And then we're going to move the stack pointer into the base pointer. So the register is pointing to this memory location. All right. Stack pointer is just going to be pointed to this location also because it's the top of the stack. Next thing we're going to do is we're going to go ahead and deal with line 6 right here, the highlighted int f equals 10. So we need to make some space. So we'll subtract and make some space on the stack. I saw before that the when we were looking at the previous version that the compiler decided to reserve 16 bytes. In the previous example, so I'm going to do that same thing here. I'm going to reserve 16 bytes and just show what the stack looks like when we've reserved this extra memory. So we're going to subtract that from the stack pointer. And over here in memory, so that's going to move the stack pointer up. Let's see here, 1, 2, 3, 4. So we'll have the stack pointer there. And this will be, here, let's go 4 bytes. 4 bytes. Just like that. So we've reserved 4 bytes in 4 memory locations, so 16 bytes total. And the next thing we'll do is we'll go ahead and use one of those memory locations to store the value 10. And we'll use that let's see here, move value 10, and we'll use it 4 above the base pointer. So minus 4 EBP. Okay, so that's going to take the base pointer, go up 4, and store it right here. And there we go, that's value 10. And variable name for that location is f. And I'm just going to make a note right here that this is -4 from EBP. So I personally can remember that. Hopefully that works. All right, after we've done that, we're just going to call the increment function. So this is going to get ready for the increment and need to prepare this parameter right here. So to start us off, this is going to be the setup phase. The parameter that gets passed is actually a memory address. So it's the address of this piece right here. So to set that up, let's see, how am I going to do that? I need to push this on the stack. That means I need to have it in a register. So I need the memory address to be stored in a register. So to do that, we're going to use the load effective address. That's always a subscript L. Load effective address. And the address that I want is this one right here. I want to access that memory location. So that's -4 from EBP. And I'm going to just store that in a register. How about EAX? There we go. And then once I've done that, yeah, we've got that. Oh, I just need to push it on the stack next. My brain was cramping up for a second there. So we'll push that memory address on the stack. And now the stack pointer is right here. That's going to move it up to right here. I'm just going to jot that down as address of F. That's what just got stashed right there. Next thing, so after we've pushed it, just like that. All right, that's looking good. Okay, so then we'll call the function. So call increment. That's going to store the return address on the stack. So it's going to move the stack pointer up. Return address right there. That's going to be the top of main's stack frame. The next line will be the base pointer for the function. So we're jumping into the function at this point. Let's see here. So we'll have these same two lines going to get copied at the beginning of every function. We'll push the base pointer and then move the stack pointer up. So this is going to be there we go. Had in the wrong mode there. Base pointer gets moved to here, and this is going to be the stored main base pointer, just like that. So the base pointer is no longer pointed to right here after we do the second line. Instead, we're going to move the stack pointer into the base pointer, and the stack pointer also gets moved up when we push the return value. There we go, just like that. Formatting there. All right, looking good. Okay, so after we've executed this line, this has prepared the next stack frame. So beginning in line 3 and above, all of those, that's going to be the frame for the increment function. Everything below this, 4 through 10, is the stack frame for main. Okay, so now that we got this all taken care of, we've got the parameter there. This is the address of stored right there. What we need to do is go ahead and do this computation, and we'll do it in 3 steps, I believe. First, we need to go get the value, so we need to dereference that pointer. Then we need to increment it, so that'll be the +1 there. And then we need to go back and store it in the right spot. So, let's see here. Oh dear. Stop messing around, Mike. So this part right here is the prologue. This part will be the body. And we'll come back and do the cleanup at the end. Although there'll be minimal cleanup, this doesn't have any local variables. All right, so here's the idea. First thing I need to do is go grab the value 10 right here. I did it in 2 steps because what was actually passed to me is the address of F. So I'm going to load that address into a register, and then we'll go access the contents of the register. So to do that, so I need to move the parameter that was given to me. So that's 8 bytes above the base pointer. So higher numbers right here. This address is stored 4 bytes, then 8 bytes. So return address is at 4. The address is at 8. And we'll just stick that into a register. EAX. Okay, so now EAX contains an address. What I'd really prefer is I want the value because I need to add to it. I need the 10, not the address. So to get that, I'm going to use move, and I'm going to get the contents of a memory location. The memory location is stored in EAX. I'm just going to use the parentheses to say go get that number, and we'll go ahead and store it right back in EAX again. So right now, before we execute this line, EAX holds an address. After we execute line 15, it'll hold the 10. I hope that makes sense. I'm trying to think if I should draw. I don't think I have a good way to draw that with a in a text file. If I think of something, I'll pause the video and bring it back in. All right, here we go. So now that we've got the value, I just need to increment it. So we can just do add immediate 1 to EAX, and then I'll take care of that addition for me. And now the next thing I need to do is go ahead and store it. I'm looking right here on line 2, the highlighted star X. I need to go store it back in the right location. So I need to dereference that variable X again. So do that in 2 steps, basically the same 2 steps I did right here. I need to go get the value, that address, and then put it in the right place. So to do that, move, I need the, so this is me grabbing the address, EBP, and I'm using EAX, so let's choose a different register and we'll store this in EDX. Okay, so now I've got the address, and now what I want to do is store the contents of this in the memory location where I've got that address. So let me make sure I don't screw this up. I'm going to move the value EAX, that's got the 11 in it, and I want to put that, so in this case we want to go to a memory, so I need the parentheses EDX. I think that looks good. Sorry about that. My computer's chiming at me. Okay, hopefully the mic didn't pick that up. It wasn't that loud. At that point, we've now updated this to an 11. Don't open 11, not 110. There we go. And we're ready for cleanup and return. So in this case, this is going to be the, let's call it epilogue in a function. In this case, there's not that much to do. We didn't use any of the local variables, so there's no stack to rewind. So instead, all we really need to do is pop the base pointer. Oh, I spelled that wrong over here. So pop the base pointer. That's going to return this stored main base pointer and put it back in the base pointer. So that'll just move this back down to here. Base pointer. And then because I'm popping something, it deletes that line. Once we've done that, we can call return. That will move the return address, pop it off the stack, put it back in the instruction pointer, just like that. And return control to this line right here, line 32. All right, following that, I don't really need to do anything. There is no return value. We've done all of the things we needed to already change the variable location. That was done inside the function instead of inside of main. The only thing we really need to do now is unwind the stack and wait, I did push something on there. I need to remove that parameter. So let's see here. Actually, leave would take care of that for me also, because it's going to just reset the stack pointer to the current value of the base pointer. But just for completeness, let me just go ahead and say we will be adding, in this case, 4 bytes to ESP, and that will take the parameter that I was just finished using and remove it just like that. Okay, after that, leave. Oh, we got to set up the, almost. Move immediate 0 into EAX. This is for the return value. I just got the return value set up. Now, leave return. So the leave will take these four numbers we've reserved space for, the 16 bytes there, and just basically take the stack pointer, which is pointed to the top one, and set it so that it's pointed to the same location as the base pointer. So that's going to take these lines right here and delete them like that. And then when we call return, it's going to return control. The stack, the base pointer gets reset. The return value gets called, and that's a return value to somewhere in the operating system when we do this from main. All right, let me see here. I was just thinking it might be useful. I've got my code here, but I didn't really put any comments in. Let me add some real quick notes here. So this, we push the base pointer. We move the stack pointer to the base pointer. That sets up the frame. This is us reserving space for F. Then we store F. Then in this setup, here we are preparing the address. Get address, push the parameter on the stack. Then we call increment. This one here is remove the parameter from the stack. This is prepare to return 0, and then leave and stuff. Okay, and then up here we prepare the stack. In the body, this piece right here was get the address from parameter. And then we actually dereference to get the value. Just like that. We added one to that's going to be the increment. Then we needed to store that value back. So we need to go get the address where we wanted to store it. Get the address this time. Store in address. And then epilogue. Pop the base pointer and return. Okay, so I'm going to go ahead and take... Hopefully that didn't go by too fast. I think I'm done with this. There, now you can see all of the comments. I'm going to go ahead and copy this code into this file over here. So this is, let's see here. Just paste that in. We'll put it in as a comment. Insert. So that it'll all be in one place when you guys go to like download the file. You can see all of the work I did right here. Comment. Hopefully this is a little higher quality than the last time. I went through it kind of fast. Using pointers is just a matter of getting the addresses, using these parentheses to dereference them. Yeah, okay, I think next up I want to go ahead and take a look at what the compiler produced, and we'll just compare side by side to what I got. One second while I go prepare that. All right, I just went ahead and ran the compiler, and if you didn't jot down the commands to come up with the abbreviated assembly code version without all of the assembler directives in there, I just wanted to give you pause on this screen, jot down this, so as you guys are going through your own examples, you don't have to worry about all the commands at the beginning of the period. The fno asynchronous unwind tables, fno pi, and fno stack protector are the three that I'm using here. All right, and then I'm just going to open up both of these files in Vim, and we'll take a look at them side by side. So I copied and pasted my best guess as to what the assembler is going to, or the compiler is going to do when it produces the assembly code. I've got that right here. And then over here on the right side, this is the actual product of the compiler proper. So if we compare, let's see, we've got main. Again, they always begin with this push the base pointer, move the stack pointer into the base pointer. Then we're going to reserve some memory. In this case, it did 16 again. I guessed 16 because we only needed space for 1 byte, or one integer, so 4 bytes, but it prefers to have things lined up neatly. So it's going to reserve 16. Then we move the 10 into the same, exactly like I did. Then we load the address 4 from the base pointer into a register and then push that on the stack. Could have used any of the registers. They chose this one. Then we called the function. After that, when we're all done with the function, we needed to remove that space from the parameter. So this is removing the parameter, and then prepare for return. Okay, so exactly the same as what I came up with. And then in the increment function, they did do something a little different. I'm seeing a load effective address here. So let's take a look at what they did. Again, we began by pushing the base pointer, moving the stack pointer in. So this is to prepare the frame. Then in the body, we grab the parameter. That's the address. Put it in a register. Access the value. Same thing I did right here. Grab the value, store that in a register. And then I just called add1 to increment that. They are doing using the load effective address command instead as a way to do the same thing. Okay, so this load effective address is frequently used by the compiler to just do simple math. It can add numbers together and scale them. In this case, the %EAX here is the value 10, and this is just computing 1 plus, it thinks this is an address when it's doing it, but it's just using the number 10. It gets the value 11 and then stores that in this register right here. So load effective address. The book actually spends a paragraph talking about how they frequently use it for just regular math. I'm not sure if it's more efficient than using add. There's probably a good reason they chose to do it this way, but I'm not sure what it is. All right, after that, the rest of this code looks pretty much the same. They stored their result in register D, and I stored it in A. So a slight difference with the choice of registers. Then we're moving, so we need to go figure out where to store this. So we go back to the stack, we grab the parameter, which is an address. They're starting it in EAX. I was storing my result in EAX, so I was using EDX for that. And then we're going to move the result into that memory location. So again, we've got things in different registers. It's design choice, I guess they're slightly different. So these should be reversed, E and D, and they have D and A. Looks good though. And then we're finally ready to return. NOP just stands for no operation. Sometimes that's used to help line things up with the binary so that the bits fall in the right spot. And then, just popping the EBP to prepare to return. So this is going to restore the base pointer so that it points to the base of the previous frame, the frame for main that is. And then it's going to return. All right, I think that's going to wrap up this example. I've got one more that I want to do, but I've got office hours in about 10 minutes it looks like. So I'm going to come back after I finish my office hours and record the next section. I'll be right back. All right, guys, I've got the third problem from the worksheet pulled up. This one is asking us to take a look at strange.s. And here's the contents of that file right now in the middle column here. And to just turn this assembly code back into C. See if we can figure out what code was used to produce this. I'm going to go ahead and just, I want you guys to try this. I think you've learned enough at this point about how assembly is generated that you could probably go backwards. So go ahead, give this your best shot, and then come back and I'll go through my solution and we'll talk about it. All right, so go do that now. All right, guys, welcome back. I'm just going to go through this assembly code here in strange.s and turn it into C, walk through it, and develop the C code. And I've got my stack over here on the right. So I'm going to start out by just sort of scanning the file and taking note of a couple big features. As I'm trying to figure out what this is doing, I need to know what's going on. I see here I've got a label for strange. That's going to be a function name. I've also got a label for main. Of course, every C program needs to have a main function. So that's those are the two functions. That's all we've got. All right, next up, let's take a look at main real quick. I can see I've got some like beginning set up the stack stuff. I've got a subtraction. Just without even looking at those numbers, that's likely just a moving, arranging for some space on the stack. Yeah, there it is, ESP. We're making some space. We're going to move some data, immediate values, onto that stack. And then it looks like I'm seeing two push operations right before the call. So here's where we call strange. We've got two push operations. That likely means there are two parameters to the function strange. After the call, we add, and we're removing 8 bytes from the stack. So that's likely parameter cleanup. We do some moving. That one looks like getting ready to return. Leave return. Okay, so main looks pretty straightforward. Then let's take a look at strange real quick. Just scanning these things. I've got my push and move for the stack setup. I'm doing something with the stack pointer. So it looks like I'm reserving space for locals. Some moving. Here I've got a multiplication. So this function is going to be doing some math. Some more moving around. And addition, because this does not look like it involves the stack. There's a register, so there's an addition going on. And then we move some more stuff around and we leave. All right, so what do I know already? I know I've got a function strange. It likely has 2 parameters, int A, int B. I'm going to guess they're int. We'll come back and check that out in a second. Let me see. What do we know about the return? Did we push anything into EAX? We did. We put something into EAX. So I'm going to guess that we're returning an integer. All right. And then, what do we know about main so far? Just from what we got, we know that prototype for main pretty much always looks like that. I know I'm declaring some local variables because I've arranged for space on the stack. And then I push 2 things, and then I call the function strange. So strange, and that's got 2 variables in it, x, y. I'm guessing they might be pointers or references. So we'll do that. And then, do we do anything after that? It looks like, yep, here's that return value. So I'm looking at line 39. So here's the call to strange. I'm just wondering, do we just call it or do we store that somewhere? So the next thing after the call to strange is to recover the parameters from the stack. And then I'm moving a return value into somewhere in memory. Okay, so that means that I've got a third something that gets stored. All right, so that's just my skimming over the program very briefly, trying to figure out a little bit about this function and the parameters. Now let's take a little bit deeper dive into this. So first up, my stack here, the very bottommost piece is going to be EBP. So this is the bottom of main. And the value stored in EBP when we begin is the operating system base pointer when this function ends. All right, then we do a little bit of setup, and then we're going to reserve space. So I'm looking at this highlighted line right there, number 31, for 4 bytes on the stack. So there's 1, 2, 3, 4. Move the stack pointer up to there. All right, and once we've reserved that space, it looks like I'm moving some immediate values in. So let's see what we've got here. 3 gets pushed 12 bytes in front of the base pointer. So there's 4 in front, 8 in front, 12 in front. Right there, we're going to store the number 3. And then it looks like we're storing the number 4 bytes in front of that. So we've got a 3 and a 4. And I'm just going to go ahead and say that these are, I'm going to guess they're integers. Int x equals 3. Int y equals 4. And so I'm just going to label these over here. This is my x, and this is y. All right, how does that look? The next thing we're going to do is, sorry about that. That was just me forgetting to mute the volume. Okay, so where did I leave off? We just moved the 3 and the 4 into those variables. I've got them labeled right there. The next thing we're going to do is we're going to push a value onto the stack in preparation for this function call. So right here we're pushing 4 off. That's going to be pushing y. So in this case, I'm going to store 4 right there. That's going to correspond to this b when we get up there, because the values are pushed right to left. So that'll be b. The next thing we do, load effective address. We are actually grabbing this address right here where the 3 is stored. So this is the address of this thing, and I'm putting it in a variable, and that's what's getting pushed. So the next thing that's get pushed is the address of x. So this is going to be, and that gets pushed. This is not actually x. We need address. Whoops. that much, address of x. So interesting. That means up here, a here is actually going to be a pointer as I go through, because I'm pushing an address that needs to go into a pointer. We'll verify that it's actually used as a pointer when we get up to the function. This is my best guess, just based on what I'm seeing as the stack preparation. All right, cool. And then after we finish up with, so we'll call strange right here. After we finish with strange, we'll remove these two things from the stack and then take care of assigning something to this variable right here. And it's actually stored at 8 away from the base pointer. So this is going to be where I've got my z, just z. All right, looks good. All right, so let's go ahead and take a look at the function call now. So when we call the function, we've prepared all of the variables. The stack pointer will be up here on that line. When we call the function, we'll get a return address stored. That will be the top of the frame for main. And then we do this stack setup stuff. We'll push EBP, and then we move the stack pointer into that. So this will be the stored EBP, the base pointer for main. Yep. And that will be, then the next line, line 8 right there, stores the stack pointer there. All right, so it stores the base pointer. Moves the base pointer to point to that line right there. Just like that. Okay. So the next thing we're going to do is we're going to reserve some space for local variables. So we'll need let's see, what do we do here? We're going to reserve 16 spots. 1, 2, 3, 4. Looks like I didn't quite leave enough space. So 1, 2, 3, 4. That moves the stack pointer up to there. Then we're going to move something 8 above the base pointer. So return address, that's going to be the address of x. That's the first parameter is 8. We're going to move that into EAX. So I'm just going to start making a few comments right here. Reserve space for local variables. This is going to get address of A, where A is stored, and this is going to dereference it. So we're taking, so now EAX has a memory address in it. Using the parentheses says go to that memory address, get what's there, and then store that back in EAX. So this is the dereference. So I just dereferenced, and let's see, address of X, I called it A. So the first thing we're doing is we're dereferencing A. Now that's stored in register EAX. All right, next thing we do, we go 12 above the stack pointer. So there's return address 4, 8, 12. That's going to be the number 4, or also known as the variable B. Let's see here. My comment right there, I wrote it as X. I called it A in the function. Just a quick note. Okay, so we're going to go grab, where did I leave off? Right there. The 4, or B, store that in EDX, and then we're going to multiply those two together. So that's times B, dereference A, multiplied by B, and then that's now going to be stashed in EAX. So this is get B, this is multiply, so A times B. So the next thing, and that's, so we're going to move EAX into -4 from the base pointer. Right here. So this is the local variable we've stored. So in this case, we've got new variable. It's going to be an integer. We're storing, let's just call it C. And let's see, what are my numbers here? I've got 3 times 4, so that's going to be storing a 12. We'll call that C. So this is going to be int C is equal to that computation. All right, looks good. Next thing we're going to do, where did I leave off? We just stashed that on the stack. Next thing, we're going to go back and get another piece of data and store it in EAX. 8 below the base pointer is 1, 2, this is that address again. Okay, so I just grabbed the address, so that's A. The next line down, we're going to dereference it. So here, this is store in C. The next line here is get the address. Then this line is dereference. And then, so we've just done this. We've done star A, 12 above the base pointer. So there's 4A. 12 is now getting B again. I'm going to store that in EAX. And this is where we're doing the addition. So this is getting B, add them, reference A plus B, add them together. Okay, after that, we're going to be looking at 8 off the base pointer, moving that into a register. It looks like we stored the result of the addition in D, and we're going to go get a, let's see, that was 4, 8. That's that address again. So I'm getting address, and again here, I'm using, so the parentheses around a register means go to that memory location and do something with it. In this case, we're storing, moving D into that position. Okay, and EDX, D was the result of that addition, and it looks like we're storing it in that memory. So that's going to be dereference A gets the result of that computation. So this star A plus B was stored in D. I just dereferenced right there. That much is dereferencing A, and I'm storing EDX back in it. So let's see, that was 3 plus 4 should be 7, stored back in A. Dereferenced A, that's also the same as X. So this is now going to be 7. All right, finally then, let's see, that was, yep, that was that line right there where we did the storing. Now, nope, that line does the storing. Here's where I'm dereferencing with those parentheses. Then we're going to move 4 from the base pointer into EX. Oh, this is getting ready to return. So, return, and what I'm going to be returning is, let's see, the local variable that has that 12 in it. Return C. I'm feeling pretty good about this. So leave then, at this point, we'll take, so we reserved all, well, basically 16 bytes worth of space. This leave will remove this, rewind the stack pointer, delete all of that stuff, and then return will take the stored base pointer, restore it to down here where we've got it at main, and jump to the return address. So that's going to take off 2 more lines from the stack, and then we returned. Back in main, we're just finished this call strange line. Now we're going to add 8 to the stack pointer. The stack pointer is pointed to the top address. When I add 8 to it, it's going to move it down and get rid of these 2 parameters. So remove both of those. All right, after we adjusted the stack pointer right there, then in line 39, we're going to move, this is that return value. We returned C over here. We're going to store this in 8 off the base pointer. So in that case, I'm looking at Z right there. Hold on 1 second. Back up here, 12 was stored in C. That's what got, that is what was returned. So I'm going to put a 12 in right there, and then should be done with this much stuff. That much. So that's what the stack looks like at this point. I now have the 12 stored in Z, 7 in X, 4 in Y. This one was updated via the pointers. Okay, we called strange, we did that. And then just to wrap up, we're going to store 0 in EAX. Leave will actually take the stack pointer, which is right here, because we reserved 16 bytes. There's 4, 8, 12, 16. And it's going to take the stack pointer and point it back down to EBP. So that's going to clear out all of those. And then return will pop the base pointer off for us. And wait, leave also does the pop the base pointer off. Return will make the jump back to wherever the operating system left off. All right, let me just, you guys have probably been screaming the whole time looking at that. I left off some semicolons just to make sure the C code looks good. We need a return 0. Oops, that's replace mode. Make sure I've got my 4 spaces. 1, 2, 3, 4. Okay, that looks good to me. Looks good, looks good, looks good. All right, so I'm going to go ahead. I'm going to save this. Yep, save it. We'll quit. And I'm going to go and compile this and see just how close it comes to this version of it. So one sec, I'll go take care of that, and we'll be right back, and we'll put them up side by side. We'll see how close this is to what I'm getting from the worksheet. One sec. All right, just so you can see what I did, right here I've got strange.s, and I'm moving it into strange commented.s, so that's the one where I made those comments, not the ones on the worksheet. Then I compiled with all of these options to like turn off all of the assembler directives to make it a little easier to read, so we just get the x86 code. Then I'm opening up strange.s, that's produced by this line where we compiled it, and I'm going to compare it side by side with the commented version. Okay. So here we go. This is the one without comments. This is the one with comments. So I'm just going to compare side by side, create 16, and make sure that I'm getting a very similar looking assembly code. Do I see any differences? I'm down. So far, so good. That looks all right. EBP, da 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 da. Push 3, push 4, 12 and 4, minus 4. Call strange. All right, from what I can tell, it looks identical. This has a bunch of comments in it. This one has the exact same commands. I might have overlooked something. I just skimmed real quickly, but I think it looks like we've got the right answer here. Hopefully you guys enjoyed this kind of material for the lecture. I think getting practice doing these things is very important. The next homework assignment is actually going to look very similar to what we've got going on with this worksheet problem 3. The next homework assignment, I'm giving you some code that's been compiled and asking you guys to decompile it. Let me show you how to do that real quick, just as so it's part of the video. So for example, right now I've got strange here. This has already been compiled. If I were to just do obj dump with the D option, I can put in strange, and this will decompile it, disassemble the file, and produce the assembly code based on the machine code that's available. So the next homework assignment is actually going to involve you guys going, disassembling, or decompiling, what's the right word for that, some code, and figuring out what it does. It's going to be a cool project. I really enjoy this one. So let's see, it's already 4 o'clock. I'm going to go ahead and wrap up this video. Yep, I'm definitely going to wrap this up right here. I just took a look at all the little clips. They definitely add up to more than an hour of footage. So that'll do it for this worksheet, for this entire lecture. To wrap up the week, I still have 3 more topics I want to talk about. How assembly deals with arrays, structures, and then some security things where we look at like stack overflow errors, buffer overflow attacks, things like that. This is probably the best place of any CS course to put that. So I don't want to like miss that opportunity. And that's going to wrap it up for the week. So as far as right now goes, I'm going to go turn this into a video, put it up on YouTube this evening, get project 4 ready to go and deliver it to you guys. And then tomorrow I'm going to put the rest of those videos together, probably in reasonably sized pieces. I'll record the array part and then see how long it is and decide whether that's its own video or not. Anyway, have a great day, guys, and hope you enjoyed this. Let me know if you like this style where I'm just going through problems. It's hard to know. I'm here in the office with a sticky desk. Yeah, my kid was taking online coding this morning, and I never cleaned it off. Yeah, just let me know. I'd love some feedback on whether this is useful or not. All right, have a great day.